In this video, I'm going to talk about polar covalent bonds and dipole moments. So what makes a bond polar? A bond is polar when there's a large difference of electronegativity between the two atoms that make the bond. So the next question is, what's electronegativity, right? All right, so electronegativity is an atom's ability to pull electrons toward itself. And electronegativity can be predicted by the periodic table most of the time, and it increases to the right and up, and we do not consider the noble gases for that. So it increases this way. And if we look at the periodic table, right here, we can see the values of electronegativity. So if I look right here, the value for fluorine is 4, and it's the greatest. And so it's increasing going this way and going this way up the periodic table. And if you look, there's a very large difference between fluorine and, let's say, potassium. And so that's why when potassium and fluorine decide that they're going to make a bond together, it is ionic. Because fluorine is so electronegative and can pull so much of the electrons towards itself that it actually pulls one away from potassium, because potassium is not electronegative enough to keep its electrons. So that's why whenever you have a metal and a nonmetal, it forms an ionic bond, because nonmetals, all of these, right, have a very, very high value for electronegativity. So you really just have to know the trends in electronegativity in order to determine if a bond is going to be polar or not. And so really pay attention to this top line right here. If you look here, fluorine is 4, oxygen is 3.5, nitrogen is 3, carbon is 2.5, and boron is 2. And so they decrease by units of 0.5 as you go that way on the periodic table. Now going down, we have 4, 3.0, 2.8, which is pretty much close to 3.0, and 2.5. Okay, and then there's 2.5 here, and there's 2.5 here. And then 2.1, 2.4. So you don't really have to memorize them. You just kind of have to know how the trend is going so that you can compare different atoms to each other in covalent compounds in order to determine if the bond is going to be polar. And most of the time, in most textbooks, it says that if the difference in electronegativity is greater than 0.4, then it's going to be polar. So let me shrink this back down and write that down here. If the difference in electronegativity is greater than 0.4, some say 0.45, some say 0.5, but I've seen as low as 0.4, then the bond is going to be polar. You can actually predict if a bond is going to be ionic if it's greater than 2.0, the difference. But we're not going to get into that because this is typically just about polar covalent bonds in this video. So if I scroll down here, I have an example to look at. Which of the following bonds is the most polar? So in question 1, we're looking at HF, right? HCl, HBr, and HI. And so if I remember right, HF is on the top of the periodic table. Let me grab my periodic table and bring it down here. And so we've got HF, HCl, HF, HCl, HBr, and HI. And so F is the most electronegative. And so the bond that it's made with hydrogen is going to have the biggest difference of electronegativity. And so that bond is going to be more polar than HCl, which will be a little bit more polar than HBr. And then HI will be the least polar of those. Okay. So now of these bonds down here on number 2, we have carbon oxygen, carbon hydrogen, and carbon chlorine. And so I know that hydrogen is all the way over here on this side of the periodic table. Now with hydrogen, it's a nonmetal, but it's on the side with the metals, so it doesn't necessarily follow this trend. You should pick up hydrogen and stick it right here on top of boron for this, because it's just going to be slightly bigger than boron at 2.1 instead of 2. So one thing that I can tell you is that carbon-hydrogen bonds are typically, they're considered to be nonpolar. So this is a nonpolar covalent bond because the difference is only 0.4. And then carbon-oxygen bond is a very polar bond. The difference is 1, right? So if I go back here and I blow this up so that you can see it, we've got 3.5 and 2.5, and so the difference between those two is 1. So I'm just going to write that down here. This one was 0.4, and then chlorine is 3.0, and carbon is 2.5, and so that's 0.5, and so that's slightly polar. And so this one is going to be the most polar, and then this one is the second most polar, and then this one is the third most polar. All right, so if you understand polar bonds, then you can understand what a dipole moment is. And so if I go over here to the next, what is a dipole moment? The dipole moment is the measure of net polarity in the entire molecule. So let me... Okay, so let me try to reword that. If you look here, it says pole, right? And so what you're actually looking at is you want to know if the electron density is being pulled to one side of the molecule. If it has a dipole moment, the electron density is being pulled to one side. If a dipole moment is significant, the electron density is greater on one end or pole of the molecule. So you've probably heard sometime in your life that water is polar, and so I'm just going to use that as an example. All right, if we look at a water molecule, okay, I'm just going to draw it right here. So you really need to know how to draw Lewis structures really well for this, and to be able to see the shapes three-dimensionally. So this is a water molecule, and remember that these two groups right here, these two lone pairs, are coming out at you in a Y shape and then not really in a Y shape, vertically. So you have this one that's coming out towards you, and this one is going back straight into the screen. Now, I can't draw it that way because if I did, I'd have to draw them right on top of each other, and so you'd just see 2 dots instead of all 4 of the electrons. And then we have these 2 hydrogen that are going away from you into the board or into the screen. So it's really, really hard for me to be able to draw this for you. But I really strongly suggest that you watch a video over Lewis structures or 3-dimensional structures in chemistry and refresh yourself on that. All right, so with this molecule, if I were to look at each individual bond, would this bond right here, would it be polar? Yes, it would. Oxygen's 3.5 and hydrogen is 2.1, and so the difference in electronegativity is great. Most of the time, if something has oxygen or nitrogen or fluorine or chlorine in it, it's going to be a polar bond. So the electron density in this bond, right, because these bonds, they're made from electrons, and so if oxygen is very electronegative, then that means that it's pulling the electron density towards the oxygen. So I'm going to write that right here. Electron density in bond is being pulled toward oxygen. And the same thing is happening in this bond because it's the same type of bond over here, and so the electron density is being pulled up that way, right? So if this molecule, remember these 2 hydrogen are going straight back into the board, into the screen, and you have these 2 lone pairs of electrons coming out at you, right? So if these are going up this way towards this oxygen that's sticking out, right, then that means that the electron density is being pulled upward. And so you could write the dipole moment here for this. The dipole moment would be just like that. And that shows the direction of the dipole moment. And the dipole moment can actually be measured. The dipole moment can be measured in a lab very easily. There's some pretty crazy calculations we can do for some things to calculate the dipole moment. And you can also check to see how much ionic character something has by looking at its dipole moment and all sorts of crazy stuff. But you don't really have to know that. You just have to be able to tell if the bonds are polar. And if the bonds are polar, is the molecule symmetrical to where they cancel each other out? And so let me show you an example of that before we do another example here. And so if we look at something like carbon dioxide, okay, so CO2. If I draw the structure for CO2, it's going to look like this. Okay, that's the most stable form of CO2. And so now, first I have to ask, is this bond polar? Yes, it is. And it's polar towards oxygen because oxygen's more electronegative, so it's going to pull the electron density in this bond towards itself away from carbon. And so what does that do? Well, if the electron density is being pulled towards oxygen, that means that it's going to be slightly negative over here. And the reason it's slightly negative is because electrons are negative. And if the electrons in this bond help balance out this molecule and they're being pulled more towards oxygen, that means oxygen is going to be slightly negative, which means that carbon is going to be left slightly positive. from this thing, and that's why we draw this positive, and at least I think that's why. That's why we draw this positive end on the arrow to show the dipole moment. Now, the same thing is happening here on this side. And so if you remember, the VSEPR theory predicts that this is going to be linear, right? It's going to be completely 180 degrees from one around this carbon right here. This 180 degrees apart, because it's the furthest apart they can get. Then that means that these two dipole moments here are going to cancel out, or the two polar bonds. And if the dipole moments or the polarity cancels out, then the molecule is nonpolar and there is no overall dipole. Okay, so if we go back and we look at water, see, these didn't cancel out because overall it's being pulled, the electron density is being pulled upwards towards oxygen. All right, so let's look at these examples that I have written down here. All right, it says, which of the following structures has a dipole moment? If it has one, indicate the direction. So the first we have written here is SF6. Okay, and SF6 will look like, it will look like this. Let me make some more room here. We're going to have sulfur and fluorine, 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 right? And so you have this square that goes around the middle, and then you have two fluorines, one going up and one going down. And then each fluorine has to have 8 electrons. And there's 48 total. And so if we distribute them all, that's what it ends up looking like. All right. So first you have to ask, are these bonds polar? Yes, this bond is polar. They're all polar. But if this is in a square around in the middle of it, then if this is pulling this way, and this is pulling this way, and this is pulling this way, and this is pulling this way, then they cancel out. And the same thing happens here on the top and the bottom. So all cancel out, and there is no dipole moment. All right. So B is H2C double bond CH2. So if I draw that in 2 dimensions, or if I draw that here as a Lewis structure, oops, then you end up with this. All right, and so is this bond polar? Well, there's a slight pull here, and here, and here, and here, I suppose. But still, this really isn't considered a polar bond, and there isn't anything in here to make a polar bond, so this is nonpolar. And so there's no dipole. All right, and then C, what do I have here? CHCl3, okay, that's chloroform. And so if we draw that, I've got carbon, let's see, hydrogen, nope, that should be chlorine. chlorine, chlorine, chlorine. And so there would be an overall dipole moment in, it depends on which way you really look at this, but you could draw it like this, towards this chlorine because it doesn't get, oops, let me see, towards this chlorine because it doesn't get canceled out by that hydrogen. Or you could actually draw it at an angle like this or like this. It depends on if you're looking at it in 3 dimensions or not, and if you're looking at the vectors. So I strongly suggest that you get and make a model set of tetrahedral structures and look at them so that you know if it's how the structure is supposed to look. So if you turn this, right, you turn this 90 degrees to where this chlorine is coming out towards you and this chlorine is going straight into the thing. That is what the molecule looks like. And so if this is coming straight out towards you and this one is going back into the board, then there's going to be a pull going upward, and then there's going to be a very large pull going between these two out this way. And so it's just a matter of what cancels out what, and where the dipole moment will go. All right. So let's see what else is up here. CH2Cl2. And so with this one, remember that this chlorine right here is actually up towards you, and this one is going back into the board while these two stay flat. And so there is going to be a dipole moment going overall this way between these two right here, because these two bonds right here, this one and this one, are polar. And so the electron density in these bonds are being pulled towards chlorine, which will make it slightly negative on this end, and then slightly positive here on the carbon. And so because there is a slight negative charge on one end of the molecule and a slight positive charge on the other end of the molecule, that makes the molecule polar. When the molecule is polar, there is a dipole moment. Oh. When the molecule is polar, when the overall molecule is polar, there is a dipole moment. Will all molecules be polar? No. Will all molecules with polar bonds be polar? No. But if the molecule overall is polar, there will be a dipole moment. All right, and the last one that I'm going to go over is CH3NH2. So it's written like this. And if we draw it out, I'm going to have carbon with 3 hydrogens on it, and then nitrogen with 2 hydrogens on it. And so if you remember from Gen Chem 1, this right here is a trigonal pyramid. And so you've basically got a nitrogen up here, and then you have these 3 things going down into a pyramid, H, H, and then carbon. All right. And that's because this lone pair of electrons has to squish these bonds down because they don't want to be close to each other because the bonds are made from electrons too. So this nitrogen right here is the most electronegative atom in this whole molecule. So it's pulling the electron density of all the bonds that it's next to up towards it. So all these bonds are going to be polar. And since all of these are being pulled upward, then there's going to be an overall dipole moment going upward. Or even you could draw it like this. So it's going in this general direction, if that makes sense. And so you could draw the dipole moment doing that. And we put a positive end on this end to represent that it being positive on that end and it being more negative on this end. And so if you think about the implications that that has to have, you're not going to have just one of these molecules in a container. You're going to have tons of them. And so if one end has a negative charge right here, and then the rest of this is positively charged somewhat, then that means that there's going to be an attraction between the positive, the somewhat positive charges, and the somewhat negative charges on the other molecules that they're sitting next to. And that's what the next video is about. It's about intermolecular forces and how molecules are attracted to one another. I hope that this helped you understand the words that you're reading and looking at, and at least gives you a place to start whenever you're working these problems. Just make sure that you can draw the Lewis structures in order to be able to analyze the information. If that's where your problem lies, there are tons of videos online about drawing Lewis structures. So if you need some help with that, make sure that you start there. All right, good luck, everyone.